take a look at an example involving a hypothesis test and a follow-up confidence interval. So a 2012 survey of 2,254 American adults indicates that 17% of cell phone owners do their browsing on their phone rather than a computer or other devices. Okay, so writing down some of the things that it's given me already here. This is a survey, so I'm looking at a sample. The sample size is 2,254. My sample success rate is 17%, and this is for Americans. If my success rate is 17%, then my failure rate is going to be 83%. Part A, according to an online article, a report from a mobile research company indicates that 38% of Chinese mobile web users only access the internet through their cell phone. Conduct a hypothesis test to determine whether this data provides strong evidence that the proportion of Americans who only use their cell phones to access the internet is different. That's a key right there, is different than the Chinese proportion of 38%. So there's a claimed value being made. The claim is 38%. And we want to test if it's different. So for the alternative, I'm going to have not equals. If it said less than claimed, I would have less. If it said greater, I would have greater. This says different, so I'm testing a two-tailed test. It asked me for the test statistic, that's my z-score, the p-value, and the conclusion and context. And we've got all the information we need here to do this test, so let's make our overhead bigger, and let's check this out together. Okay, first step, hypotheses. Second step, my model. P hat is normally distributed with the center of P and the standard deviation of root PQ over N. P hat is the name of the model. We're working with proportions. Capital N stands for the normal distribution. And your model is always based off of the null hypothesis. So I'm going to plug in this 0.38. This says P. I'm plugging in the value for P. That's 17% success rate for Americans. We're going to use that later. If my success rate is 38%, then my failure rate is going to be 62%. They're complements. And my sample size was 2,254. That's a decent sized sample, so I would not be surprised if I end up with a pretty small standard deviation. This first number represents the center of my curve. Second number will represent my standard deviation for the curve. And I've got the square root of 0.38 times 0.62 over 2,254. And this gives me a standard deviation of 0.0102. 0.0102. If I'm drawing the picture, the center of my curve is always going to be the claim, 38%, and I'm roughly counting by about 1%. So that would be 37 and 39. The third step of a hypothesis test is to calculate a p-value, and the p-value is the likelihood, we're looking at a probability of something, of our sample data. Well, our sample data was a 17% success rate for a sample, or more extreme. So I'm using whatever symbol I've got on that alternative hypothesis, two-tailed test. If the null hypothesis is true, I'm putting the 17%, oh dang, 17% on this curve is going to be way, way out there. And I'm going to shade two tails, but it's hard to shade two tails here because it's super, super far away. Even from my picture, I can see that my p-value is going to be 0 plus. It's going to be a remarkably small amount of this curve that's shaded in. I still want to go through the process of finding this to verify that, though. So let's find our test statistic. And that's just a fancy way of saying our z-score. Our z-score is our data value minus the center divided by the standard deviation. The value is coming from our data, 17%. The center is coming from our model, 38%. That's our claim. And our standard deviation is 0.0102. Already, I can see that this thing is way, way off the charts rare. So I'm not going to be too alarmed if I get a weird looking z-score, for example, negative 20.59, because it is a long, long ways away from that center. If I try to look this thing up on a table, since this is a two-tailed test, my p-value is going to be 2 times that tail to the left. I'm going to see that my smallest z-score is negative 3.49. And I already have 0.0002. It's going to be way, 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 way smaller than that, though. So my value is going to be like 0.0000 repeating. Well, if I have such a small value, if I multiply it by 2, it's not going to change anything. It's still going to be really, really close to 0, 0.0000, some minuscule value that we call 0 plus. When your z-score is off the chart, you're going to have these really weird, tiny, tiny probabilities if you're looking at a two-tailed test. And I can verify my result here inside of GeoGebra, and I will in a second. But let's do our conclusion. While we can choose our alpha, kind of doesn't matter too much in this case. I'll just use 5%, because this is so much smaller than pretty much any alpha level that you would pick, which means since our p-value is low, the null must go. We'll reject the null hypothesis. Rejecting the null hypothesis means you have evidence of the alternative. So we have evidence. The American cell phone web usage proportion is different than China's rate of 38%. So a follow-up question to this might be, okay, it's different than 38%, but what should I expect? And that's the next part of this question. It says calculate a 95% confidence interval. So if I wanted to make a 95% confidence interval for p, then I'm looking at p hat plus or minus my critical value z star, square root p hat q hat over n. In the previous problem, both my tails, I had an alpha level of 5%, so it makes sense to use 95. 5 and 95 are complements. For p hat, I'm not plugging in the claim of 38, I'm plugging in the sample data of 17%. So I'm going to have 0.17 here, plus or minus, if I want to be 95% sure, the critical value is 1.96. My success rate is 17%, so my failure rate is 83%, and the number of samples was 2,254. And I should see this interval is substantially lower than 38%, because I had a lot of evidence that was less than 38%. So if I type this in, 0.17 minus 1.96, square root 0.17, 0.83 over 2,254, I get a low value of 15.4%. Changing that minus to a plus, gives me a high value of 18.6%. So we are 95% confident that the American rate is between those numbers being 15.4% to 18.6%. Now I want to use GeoGebra just to double check my values before I type anything into MyOpenMath. So I've gone to geogebra.org and I've chosen the option for Classic. I like the interface for Classic. And I'm going into probability. This gives me a normal curve. And if I choose this option with the brackets pointing out, it will shade my two tails. And I'm going to type in my z-score of negative 20.59. And my other z-score would be the same thing, but positive 20.59. And you'll notice that inside of GeoGebra, it's giving me that same p-value of 0+. So I'm not too alarmed by that. Now, GeoGebra does something really nice in statistics for double-checking work. It has both a z-test for proportion. We use z-scores to analyze proportions here. And it has a z-estimate of a proportion. We're looking at a confidence interval or an estimate of a proportion down there. So for the test, we had a claim of 38%. And the number of successes, they didn't give me the number, it was just 17%. But that's 17% of that 2,254. So you could always multiply that together to get the number of people that were considered a success. In this case, that's about 383. For the sample size, I had 2,254. Doing so verifies my test statistic of negative 20.54, so up to a little bit of rounding. That's what we're getting there. I'm going to write down the calculator later one side by side. It is giving me the same p-value of 0+. Now let's check out the z-estimate of a proportion. And you'll notice that it copies my numbers over. It assumes that I want to do these two things side by side. Hypothesis test told me that the rate was different than 38%. This interval of 15.4 to 18.6 is telling me how that looks different. Let's type these into MyOpenMath. I'm testing for a difference. My test statistic was negative 20.59. I'm going to try it with the 9 and see how picky it is. If it's really picky, I'll change it to the 4. My p-value, I had 0.0000, super small. Since our p-value was less than our alpha, we rejected the null hypothesis. And we shouldn't say except, we should really say that we have evidence of the alternative. In particular, the data provides sufficient evidence that the proportion of Americans who use their cell phone to access the internet is different than the Chinese proportion. On the lower end of my interval, it says use 4 decimal places. Okay, so for 4 decimal places, I had 0.1545. And for the upper, I had 0.1855. And we can be 95% that our confidence interval contains the sample proportion. So our conclusions are about populations. I plug in samples and it tells me about population. So I don't want that. 95% of Americans use their cell phones to access the internet. No, it's probably closer to like 15 or 19%. We can be 95% confident that the proportion of Americans who use their cell phone to access the internet is contained within our interval. That looks great. So this is what I should have here for this MyOpenMath question. Checking this, it did get a little bit grouchy with me for that negative 20.59. So let's use the GeoGebra answer of negative 20.54. A good way to fix this is use more decimals to your standard deviation. And doing so would fix that problem. I get negative 20.54. Again, I just want to show you how I could have gotten the same thing if I just used some more decimals early on. So my standard deviation from earlier with some more decimals does give me this negative 20.54. So this was really a round off error. That was why I was getting a slightly off value compared to GeoGebra. If you use more decimals, you will get more accurate. Hope that helped here for this question, looking at an example of both a hypothesis test and a confidence interval. As always, I'm available for questions.